A digital filter in the form of a direct form FIR structure is shown here. As you can see, we have z minus 1, z minus 1, z minus 2, z minus 1, and z minus 1. So it's total 6-order FIR structure that is shown here. Now, we want to show that it is possible to realize this in a cascade format as a part of Cascade Design, and it's equivalent to these two segments of a Cascade Design. I'm highlighting them. Effectively, we are saying that show that you can implement this filter in cascade format using two smaller FIR filters, and then find the system zeros and poles. Okay, to do that, we need to first find the difference equation of this FIR filter that is given to us. Let's do that. We know that I'm going to deal with this multiplied by 2 later, but what are we seeing here is effectively I am having 2 times xn minus 1, and here we are seeing 2 times xn minus 2, and then here we have, be careful, it's negative 2, so it's 2 times xn minus 4, and finally here and at the end we have 2 times xn minus 5, and then at this node we have 2 times xn minus 6. So with them in mind, given that we are all multiplying these samples with the corresponding coefficients that are shown here and then add them up together in this chain of adders to find the output sample yn, I can write yn is equal to, as you can see, 2 times x of n is multiplied and then added to everything. So 2 times x of n, and then we have negative 0.8 x of n minus 1, and we have 0.64 x of n minus 2, because I already factored out 2 and I have written it outside the close bracket, so plus 0.64 x of n minus 2, and then the same thing, we have negative 1 and x of n minus 4, 2 already factored out, so negative x of n minus 4. Okay, and we have 0.8 x of n minus 5, so let me just move, okay, we have 0.8 x of n minus 5. Finally, we have negative 0.64 x of n minus 6, and 2 is again factored out outside, so minus 0.64 x of n minus 6. Okay, and then what we need to do is I am going to close the parentheses or close bracket here, and then I can write, now that I have the difference equation, so this is what is known as the difference equation. Let me highlight it here. So this is my difference equation, which shows the relationship between output and input of this system. Now, I am going to use the Z transform to this system, to this difference equation. So applying Z transform, naturally I'm going to get yz on the left hand side equal to 2 times x of z. And then, of course, let me factor out x of z so that I don't end up writing it multiple times. So minus 0.8 z minus 1 plus 0.64 z minus 2 minus z minus 4 plus 0.8 z minus 5 minus 0.64 z minus 6. And the whole thing is, of course, multiplied by x of z. So 2 times x of z equal to y of z. Okay, so this is, now I just need to say, okay, h of z is y of z over x of z. This is the system transfer function. And just to summarize, what I got is, I'm going to just copy paste what I've written here. So 2 times, and then I can copy paste this whole thing. Great. Okay, so this is what I got. Let me just make sure that you can see it. All right. So this is the outcome. All right, so this is the transfer function of interest for this problem. And let me highlight that as well in this format. So this is the resulting transfer function that I wanted to show for this system. Now, interestingly, we can factor out components here. As you can see, it's interestingly in the form of 1 minus 0.8z minus 1 plus 0.64z minus 2, and then again negative z minus 4 plus 0.8z minus 5 minus 0.64z minus 4. So if I keep 2 outside, it's as if I name this as, let's say, p of z, then I can say it's effectively p of z minus z minus 4 p of z, which means it's 2 times p of z times 1 minus z minus 4. Very interesting. So this transfer function of interest is effectively equal to 2 times, or let me put it this way, is effectively equal to 2 times 1 minus z minus 4, and then p of z is 1 minus 0.8 z minus 1 plus 0.64 z minus 2. All right, that's exactly what we needed, because if you take a look at what I just obtained, this first portion, this portion, 1 minus z minus 4, is exactly what is implemented by, let me use a red color so that you can see it better. So is exactly what is implemented by this portion, because that is exactly 1 minus z minus 4. And then this 2 here is what is implemented, of course, by this guy. And then the last segment, 1 minus 0.8 z minus 1 plus 64 z minus 2, is exactly what is implemented by, if I use a different color so that you can see, by this portion. By this portion. So we proved that we can rewrite the transfer function in the form that is satisfying the cascade implementation. Now, the last action is finding the poles and zeros of the transfer function. Be mindful that when you want to find the poles and zeros, you have to write the transfer function as a function of z instead of function of z minus 1. So to do that, let me just highlight this. To do that, I am going to write it this way. So it's 2 times z minus 6, which I can write it as 2 times 2 over z to the power 6 times z4 minus 1 times z squared. And one interesting trick here is I can write the second portion in the form of z minus 0.8 e to the j pi over 3 z plus 0.8 e to the j negative pi over 3. Of course, generally speaking, when you have a second order polynomial, you can use any of the known methods to find the roots of that second order polynomial. So this is no different. I'm just saying that if you do that, you will end up finding that the two roots of the second order polynomial are these guys that are shown here. So what is the benefit of this? Of course, what we learned from rewriting this, and as a reminder, I just wanted to highlight that you have to rewrite your h of z as a function of z instead of function of z minus 1. Now, we have z to the 6 in denominator, so that means we have 6 poles at, so we have 6 poles at z equal to 0. Okay, and what about the zeros of the system? Well, obviously, this guy is telling us that we have 1 0 at negative 0.8 e to the negative j pi over 3 or 60-degree phase. And this one is telling us that there is a z2, which is complex conjugate of z1 in the form of plus 0.8 e to the, sorry, my bad. Let me just make sure I'm not missing something here. Okay. So be careful. It's very important to be careful. So now it's corrected. All right, so it has plus 0.8 e to the negative j pi over 3 and plus 0.8 e to the positive j pi over 3. Now it's in the form of proper complex conjugate. And the last one is z to the power 4 minus 1, which if you set it to 0, it gives you z to the 4 equal to 1, which is e to the j 2 pi. And as a result, the fourth root of that, fourth root of 2 pi or fourth root of 1 becomes, as expected, becomes 4 more zeros. And those zeros are z3 equal to e to the j pi over 2, z4 equal to e to the j pi, z5 equal to e to the negative j pi over 2, and finally z6 equal to 1. So at DC, this filter is not passing DC effectively, so it will kill the DC as seen from the coefficients of the filter. So we have 6 zeros and 6 poles, and if you're interested to showcase them now that we found them, so let me highlight them for the sake of reference. So these are 2 that I found here, and these are, let me use a different color. Okay, maybe I can do it this way. So maybe I can do it this way. These are the 2 zeros that I found originally from the first component. And these are the rest of zeros that I found here. Okay, now if you want to show the pole 0 plot, maybe I can show it here. So there you go. This is my pole 0 plot, z-plane. So in my z-plane, the way you show it is this way. You will show 6 here, so that means you're saying there are 6 poles at 0 exactly. And then we have zeros, 6 of them. One of them DC, the other one is at 60 degree, so pi over 3. And interestingly, all of them are on unit circle. That's also one interesting thing in this system. And then we have z equal to pi over 2, z equal to pi, z equal to negative pi over 2, and then we have, oh sorry, my bad, I forgot that 0.8 there. So the other one is here. Be careful that it's plus 0.8, so you're dealing with r equal to 0.8, so it's not on unit circle, it's on a circle that has a radius of 0.8. So, and the phase is negative pi over 3 and plus pi over 3, which means you're dealing with that one and the complex conjugate that is shown here. So this one. Alright, so this is roughly the pole 0 scheme for this total digital FIR filter, showing that there are 6 poles and 6 zeros. I hope that this example is helpful.